Hello Calc 3, welcome back to the second half of section 16.3. So at the end of the video for the last section, there are a few questions that are now raised. So we brought up theoretically the notion of a path-independent line integral, as well as the notion of a conservative vector field. But even if we can determine that a vector field is conservative, the question is, how can we find a potential so that we can use the theorems that we developed in the last section? And ultimately, that's the goal of this video. So this video is about finding potentials, and then at the end of the video, we'll talk about exact differential forms, which will be a little bit of a new topic, but related to conservative vector fields. Okay, so again, the two questions that we want to answer here are, how do we know that a vector field F is conservative if it's given to us? And then secondly, even if F is conservative, how do we find a potential function for F so that we can actually use the nice theorems that we developed in the last section? Okay, so let's start off first answering the question of how to know whether a vector field is conservative, and that leads to this component test for conservative fields. So if we have a vector field F, which is equal to m of xyz I plus n of xyz j plus p of xyz k, so here we have m, n, and p are the component functions for our vector field. And let's say that F is a vector field on an open, simply connected domain whose component functions have continuous first partial derivatives. So notice here we specify that the domain has to be simply connected. I think this is the first time in any of the theorems that we require the domain be simply connected. And I talked in the last video about what simply connected means. And again, the component functions must have continuous first partial derivatives for the three different partial derivatives. Then, if this is the case, our vector field F is conservative if and only if these following equations hold. And notice that this is an if and only if. So we have that if the partial of p with respect to y is equal to the partial of n with respect to z, if the partial of n with respect to z is equal to partial p with respect to x, and finally, if partial n with respect to x is equal to partial m with respect to y, then we can conclude that F is conservative. And in the other direction, if F is conservative, then these three different equations will also hold. So again, this is an if and only if statement here, a very powerful test. So we will only prove the first direction here, since the reverse direction, proving that these three equations imply that F is conservative, requires some material from section 16.7, which we won't even cover in this course. But we will prove the first direction here. So assume that we have a vector field F equals mi plus nj plus pk, and assume that this vector field is conservative, then we want to show that these equations hold. So because the vector field is conservative, we know that there has to be a potential function little f such that our vector field is the gradient of little f. And again, the gradient of little f must equal mi plus nj plus pk then. So this allows us to say that our component function m is the partial derivative of f with respect to x. The component function n is the partial derivative of f with respect to y, and the component function p is the partial derivative of f with respect to z. So we have these three different equations here, just because f is a conservative vector field. And from here, we can take the partial derivative of p with respect to y, but p is just the partial derivative of f with respect to z. So that means that the partial derivative of p with respect to y is equal to the partial derivative of f with respect to z, and then the partial derivative with respect to y. So we have a second order partial derivative here. And by a theorem that we have for mixed partial derivatives from a theorem in chapter 14, we can switch the order of this second order partial derivative here so that we get f sub yz. But f sub y is equal to n. That's given up here, which means that f sub yz is equal to the partial derivative of n with respect to z. And if you look back up at the theorem here, this gives us our first equation, so that the partial derivative of p with respect to y is equal to the partial derivative of n with respect to z. And I won't go through the other two here because they're very similar to the discussion that we just had about the partial derivative of p with respect to y and the partial derivative of n with respect to z. If you want to, you can look at these other two equations here and verify that that is the case for yourself. And again, the reverse direction requires some information from section 16.7, so I won't cover it here, but it is in fact the case that the reverse direction is true, and that will allow us to determine whether f is conservative or not relatively quickly. And once we know that our vector field f is conservative, then the next step is to find a potential function for f, so some little f that's a scalar function, such that the vector field is equal to the gradient of f. So we need a little f such that the partial derivative with respect to xi plus partial yj plus partial zk is equal to our vector field given by mi plus nj plus pk. And this equation here now tells us that m has to equal the partial derivative of f with respect to x, n has to equal the partial derivative of f with respect to y, and p has to equal the partial derivative of f with respect to z. So if we can find a little, or a scalar function, little f, such that these three equations hold, then that scalar function will work as a potential for our vector field f. So now with this new information, we can move on to our first example for this video. So we want to show that the vector field f given by e to the x cosine y plus yzi plus xz minus e to the x sine yj plus xy plus zk is conservative. So we want to show it's a conservative vector field. And then after we show it's conservative, we want to find a potential function for our vector field f. Okay, so this is really a two-step problem here. First, showing that f is actually a conservative vector field, and then second, finding a potential function. So we'll start off by showing that f is in fact conservative, and to do so, we can use this component test that we just talked about up here. So to use the component test, we're going to want to take the appropriate partial derivatives of the component functions for our vector field. So first we take the partial derivative of p with respect to y, and we get x. Again, you can verify all of these partial derivatives as I go through them just by pausing the video and checking for yourself. The partial derivative of n with respect to z is equal to x, so this is our n component here. The partial derivative of m with respect to z is equal to y, so m is this component function. The partial derivative of p with respect to x will give us a y. The partial derivative of n with respect to x will give us a z minus e to the x times sine y. And then finally, the partial derivative of m with respect to y will equal z minus e to the x times sine y. And each of these partial derivatives has been calculated in such a way that they are adjacent to the appropriate partial derivatives to use the component test. So we can see that partial p with respect to y is equal to partial n with respect to z, and that is the first equation from the component test up here. Next, we have that the partial derivative of m with respect to z is equal to y, and the partial derivative of p with respect to x is equal to y, so they're equal to one another. And then finally, we have that partial n with respect to x is equal to partial n with respect to y. And you can check for yourself that these are the three equations we need to verify from the component test to conclude that f is a conservative vector field. And so it is in fact the case that f is conservative here. Okay, now because f is conservative, we know that our vector field f has to equal the gradient of f for some little f, some scalar function. And this allows us to say that e to the x times cosine y plus yz has to equal the partial derivative of f with respect to x. So here we're taking the component function m from our vector field f and setting it equal to the partial derivative of f with respect to x. And we can do the same kind of thing for the other component functions. So the n component for f has to equal the partial derivative of f with respect to y. So you can check that there. And then we also have that the partial derivative of f with respect to z has to equal our p component from our vector field f. And again, you can verify that these equations here are correct based on the equation that we've given for the vector field in the problem statement. Okay, and this is probably the big calculational aspect of this video here. This is the thing that you probably need to know going into the homework. It's going to be a little bit different than anything you've done before in calculus, I think. So again, this is probably the most important calculational aspect of the video. So to find this scalar function little f, we can start by integrating our first equation. So when I say first equation, I mean this equation here with respect to x, in the hopes of finding an expression for our scalar function f of x, y, z. So when we integrate with respect to x, we hold y and z constant in our equation here. And if we do that, we get f of x, y, z is equal to e to the x times cosine y, because cosine y is just a constant, and the integral of e to the x with respect to x will give us an e to the x. So we have this e to the x cosine y, plus xyz, since yz is a constant, and we take the integral with respect to x. And then here is the key novelty here. So typically when we integrate from Calc 1, we would have a constant of integration, some c that shows up here. But in this case, if we had any function in terms of just y and z, and we took the derivative, then we would get 0, because y and z would be treated as constants if we took the partial derivative with respect to x. And for that reason, the constant of integration, when we're taking the integral with respect to x, is actually going to be a function in terms of just y and z. So notice that this g of yz does not have any x's that are showing up inside of the function there. It is a function purely in the variables y and z. And from here, we want to calculate the partial derivative of this f of x, y, z that we just constructed with respect to the variable y, and then match it with what we expect to get when we take the partial derivative of f from this equation up above. So if we take the partial derivative of this f of x, y, z here with respect to y, we get a negative e to the x times sine y plus x times z plus the partial derivative of this function g with respect to y. And again, we have to set this equal to the partial derivative of f with respect to y that we expect from this equation up here. So we set it equal to xz minus e to the x times sine y. And now we could add e to the x sine y to both sides of the equation here. We can subtract an xz from both sides of the equation, and we're left with the partial derivative of g with respect to y has to equal 0. And what this tells us is that g is a function of z alone. And then finally, we can now take our f of x, y, z that we've kind of been constructing. So that was the original construction, but we have this constant of integration at the end. And now we can write it as f of x, y, z is equal to e to the x cosine y plus x, y, z plus h of z. So notice here that we've taken that function g of y, z, and we've replaced it with a function that is just in terms of z, because the partial derivative of g with respect to y is equal to 0, meaning that it doesn't have any y terms showing up inside of it. So it can be written purely as a function of z. And then finally, we kind of repeat the same process. So we take the partial derivative of this concocted f here with respect to z, and compare that partial derivative with what we expect to get from this third equation up here. So we expect the partial derivative of f with respect to z to equal x times y plus z. And so we want to make sure that this h of z, whatever we choose it to be, is such that when we take the partial derivative of f with respect to z, we get xy plus z. So if we take the partial derivative with respect to z, we get an x times y plus the partial derivative of h with respect to z. And again, we set that equal to what we expect the partial derivative of f with respect to z to be. And that'll be this xy plus z here. So we get xy plus partial h with respect to z is equal to xy plus z. And again, doing a little bit of algebra, we end up finding that the partial derivative of h with respect to z is just equal to z. And then finally, because h is a function in the variable z, it's a single variable function, then to find h, once we know that the partial derivative of h with respect to z is equal to z, we can just take the ordinary integral. So because h is a single variable function, partial h with respect to z is just equal to the derivative of h with respect to z, because there's only one variable here. And we certainly know how to find the antiderivative in that case. And so we get a 1/2 z squared plus this constant of integration now, which is just going to be c. And so we can put all of this information together now. We can substitute this 1/2 z squared plus c for h of z up here. And we find that our potential function is f of xyz is equal to e to the x cosine y plus xyz plus 1/2 z squared plus c. So what does that mean? It means that if you took this scalar function f and you found the gradient should give you our original vector field. And this is, again, this is the big example of this whole video here. If you can do this calculation of finding the potential function, then you should be pretty set for the rest of section 16.3. Okay, before we move on to exact differential forms, there are a couple more examples for conservative vector fields that we should go through. Just important examples to know about. So in the first example here, we want to show that f equals 2x minus 3i minus zj plus cosine zk is not a conservative vector field. So before we showed that f was a conservative vector field, now we want to show that it's not. And again, we can just use the component test and show that the equations from the component test are not satisfied. And this is relatively easy to do. So we can just take the partial derivative of p with respect to y, and we get 0. The partial derivative of n with respect to z is equal to -1. And the component test tells us that if f is conservative, then the partial derivative of p with respect to y has to equal the partial derivative of n with respect to z. But this is not the case, as we now see. And so we can conclude that our vector field f is in fact not conservative. So proving that a vector field is not conservative might actually be a little bit easier than proving that it is in fact conservative, just using the same component test. And then secondly, here's another important conceptual example, hopefully to show why some of the preconditions are necessary for the component test. So we want to show that the vector field f equals -y over x squared plus y squared I plus x over x squared plus y squared j plus 0k satisfies the equations in the component test, but is not conservative over its domain. And then once we show this fact, we want to answer the question, why is this possible? Because it seems like it would contradict the component test, that it can satisfy the equations from the component test and yet still not be conservative. But we'll explain why that's the case. So again, from our vector fields, we have that the component function m is equal to -y over x squared plus y squared. We have that n is equal to x over x squared plus y squared. And we have that p is equal to 0. And then we can take all of the appropriate partial derivatives here. So we have a bunch of zeros that are showing up. And I guess the only interesting partial derivatives are these partial derivatives we get when we take the partial derivative of n with respect to x and the partial derivative of m with respect to y. And we need these to be equal to one another in order for the component test to hold here. And we find that they do equal one another. So in the numerator for both, we end up with a minus x squared plus y squared. You can check that. And in the denominator, we end up with x squared plus y squared, the quantity squared for both of them. And so all of the appropriate equations from the component test are in fact satisfied in this case, but we can show relatively easily that this vector field f is not conservative over its domain. And we'll give a construction here to show that f is not conservative, and then answer the question why this can be the case. Why doesn't the component test just fail here? Okay, so we can let C be a circle parametrized in the plane by r of t is equal to cosine of ti plus sine of tj plus 0k, where t is ranging from 0 to 2 pi. So we are talking about a vector field in space here, but this is a curve in the plane because k is equal to 0, and it should look something like this. So it's a circle of radius 1 that's going around the z-axis. You can think about the z-axis coming out of the page in the center there, and we're going around counterclockwise. And ultimately, we're going to show that the integral of our vector field f over this circle is not equal to 0. And remember that a vector field is conservative if and only if the integral of f around any closed curve inside of its region is equal to 0. And so the fact that this is not equal to 0 is going to cause us some problems here. Okay, so we can use methods from section 16.2 to evaluate this line integral here. So the integral of f over our circle C is equal to the integral from 0 to 2 pi of f of r of t dot dr dt dt. So this is an expression that we get from section 16.2 that we've talked about before. And so we want to find f of r of t just by substituting. And we get negative sine ti plus cosine tj plus 0k. And then we also need the derivative of r with respect to t. And that'll give us a negative sine ti plus cosine tj. And now we can substitute things in appropriately. And we get that the integral of f over c is equal to the integral from 0 to 2 pi of the dot product of these two vector functions here. And that'll give us sine squared of t plus cosine squared of t. And of course, that's just going to equal 1. And so this reduces to the integral from 0 to 2 pi of dt, which is just equal to 2 pi. And the important thing here is that 2 pi is not equal to 0. So we just constructed a closed curve inside of the domain of our vector field f, such that when we take the integral of f over our closed curve, we do not get 0. And that implies that f is not conservative. But f satisfied all of the equations from the component test. So how can this be the case? And the reason is because the domain of f is not simply connected. So if we go back up to our vector field f, notice here that we have division by x squared plus y squared in the I and j components, meaning that if we look at the origin, if we try and plug in the point 0, 0, 0, f is not going to be defined at the origin. And so if we take a loop and we put that loop around the origin, notice that if we try and contract that loop, we're going to end up at the origin or on the z-axis where f is not defined, in which case when we contract that loop we leave the region for our vector field f, meaning that the region on which f is defined is not simply connected. And if we go back up to, let me see if I can scroll back up here. If we go back up to this component test for conservative fields, notice that we specify f has to be a vector field that's defined on an open, simply connected domain, whose component functions have continuous first partial derivatives. And so in this case, we have a vector field that is not defined on a simply connected domain, and we could exploit that fact by finding a curve in the domain of f that encloses a region on which f is not defined. And once we made that curve, we find that the integral of f over that curve is not equal to 0. So again, f is undefined around the z-axis, so a loop that goes around the z-axis does not contract to a point in D. And so the component test does not apply for a vector field like this. So this is a good thing to keep in mind. The preconditions do have to be met to use the component test, but I think for most of the vector fields that we find, the preconditions for the component test will in fact be met. Okay, so now we are ready to move on to the second topic for this video, which is exact differential forms. And in many respects, exact differential forms is just an extension of the topics that we've already talked about in this video and the video for the first half of section 16.3. So often, remember from section 16.2, we can represent work and circulation integrals in differential form. And by differential form, I mean we represent them as the integral of m dx plus n dy plus p dz over some curve c. And these integrals are relatively easy to evaluate as long as m dx plus n dy plus p dz is the total differential of some scalar function f. So this is similar to the way that if we're evaluating the integral of some vector field f over c, that line integral is relatively easy to evaluate if we can write f as the gradient field of some potential function, little f. In this case, these integrals are easy to evaluate as long as this m dx plus n dy plus p dz is the total differential of some scalar function f. And so assume that this is the case, and we'll show why these are relatively easy to evaluate. So let A and B be 2 points in the domain here, connected by some curve C. And now say we want to evaluate the line integral of m dx plus n dy plus p dz over this curve C connecting A and B. Then, assuming that m can be written, or n dx plus n dy plus p dz can be written as the total differential of some scalar function f, we can rewrite the equation like this. So m is equal to partial f with respect to x dx, n is written as partial f with respect to y, and p is written as partial f with respect to z. And so we get this, the integral of this expression here. But we can rewrite that expression as just the gradient of our scalar function f dot dr. And the fact that now we can replace the integral over c with just the integral from the point A to the point B is because the gradient of a scalar function is always going to be a conservative vector field. So that's from theorem 2 of the previous video, that the gradient of f will always be conservative. And then we can use the fundamental theorem of the line integral to say that this integral here is equal to little f of b minus little f of a. And so ultimately, if it's the case that m dx plus n dy plus p dz is the total differential of some scalar function little f, then we can write the integral then the integral of m dx plus n dy plus p dz over the curve C is equal to this little f at B minus the little f at A. Okay, and this leads us to our first definition now for this section on exact differential forms. So any expression that looks like m of xyz dx plus n of xyz dy plus p of xyz dz is called a differential form. So we talked about this in section 16.2. But a differential form is exact on a domain D in space if basically, just if this differential form can be realized as the total differential of some scalar function f. So if m dx plus n dy plus p dz is equal to partial f with respect to x dx plus partial f with respect to y dy plus partial f with respect to z dz, which is equal to the total differential of f by definition, for some scalar function little f throughout the region D. So again, the point here is the definition of an exact differential here. And we have a component test for the exactness of m dx plus n dy plus p dz that looks just like the component test we had for the conservative, or to determine that a vector field is conservative. So the differential form m dx plus n dy plus p dz is exact on an open, simply connected domain. So notice here that the preconditions are equivalent for both of our component tests, if and only if the following three equations hold. And we have the same equations that we had for the component test for conservative vector fields. And this is equivalent to saying that the field, or the vector field, that is composed of the component functions m, n, and p is conservative. So that's why the component tests look so similar to one another, because we can take these functions m, n, and p and use them to create a conservative vector field here, as long as these equations are satisfied. And now finally we can move on to the last example for this video, and as well as the last example for all of section 16.3. So we want to show that the differential form y dx plus x dy plus 4 dz is exact, and then evaluate the integral of y dx plus x dy plus 4 dz from the point 1, 1, 1 to the point 2, 3, negative 1 over any path from 1, 1, 1 to 2, 3, negative 1. So if we show that this differential form is exact, then this integral here is going to be the same regardless of the path that we take from 1, 1, 1 to 2, 3, negative 1. So again, this is kind of a two-step example. We want to start out by showing that our differential form is in fact exact. So we take the derivative, or the partial derivative of p with respect to y, and we get 0. Partial n with respect to z is also 0. Partial m with respect to z is equal to 0. Partial p with respect to x is equal to 0. And then maybe the only interesting partial derivatives that pop up here, we have the partial derivative of n with respect to x is equal to 1, and partial m with respect to y is equal to 1. Again, if you want to, you can pause the video and just verify that all of these partial derivatives are correct. But after we have these 6 different partial derivatives, we can see easily enough that our differential form y dx plus x dy plus 4 dz satisfies the component test, and for that reason our differential form is exact. And now that we have that our differential form is exact, we want to find this scalar function f such that our differential form can be written as the total differential of little f. And this process here will be very similar to the process we used previously to find potential functions for vector fields. So we want to find a little f such that our differential form is equal to partial x dx plus partial y dy plus partial z dz, really just meaning that y is equal to partial x, x is equal to partial y, and 4 is equal to partial z. And here's where the process becomes very similar. So we start by taking the integral of the first equation with respect to x, and that will give us f of x, y, z is equal to x times y plus g of yz. So our constant of integration is a function in just the variables y and z, no x here. And from here, we take the partial derivative of this concocted function with respect to y, and we get x plus the partial derivative of g with respect to y, and we set that equal to what we expect to get when we take the partial derivative of f with respect to y up here from the second equation. So we set it equal to x, and now we can solve for the partial derivative of g with respect to y, and just like the other example where we did this, we get a 0, meaning that this function g of yz has to just be a function in terms of the variable z. So there's no y's or y terms that are showing up inside of this constant of integration g of yz. And so we can rewrite that f of xyz is in fact equal to x times y plus h of z, where h is now just a function in the variable z. We've gotten rid of the y. And now we can take the partial derivative of this new concoction for f with respect to z, and we just get the partial derivative of h with respect to z, and we set that equal to 4 because that's what we expect the partial derivative of f with respect to z to equal. And again, at this point, partial h with respect to z is just equal to dh dz because it's a function of a single variable. And so we just take the ordinary derivative, or the ordinary integral, I should say, and we get 4 times z plus c, where c is a constant of integration here. And ultimately, with a little bit of substitution, we have that f of xyz is equal to xy plus 4z plus c. So this is going to be our scalar function f such that our differential form is the total differential of this function f. And from here, we can write the integral of x dy plus y dx plus 4 dz as over the curve c as the integral of the gradient of f dot dr over the curve c, and by the fundamental theorem of line integrals, that just amounts to f evaluated at 2, 3 minus 1 minus f evaluated at 1, 1, 1, and we get a 2 times 3 plus 4 times negative 1 plus the constant of integration c minus a 1 times 1 plus 4 times 1 plus the constant of integration c, and these constants of integration are just going to cancel with one another. You should just cross that out. And we end up with a minus 3. So what this means is that the integral of our differential form y dx plus x dy plus 4 dz from the point 1, 1, 1 to the point 2, 3, negative 1, regardless of which path we choose, is going to equal negative 3. Okay, and that is the end of the material for all of section 16.3. I think at this point you should be prepared to complete all of the homework and any of the questions that show up on quiz 7. So email me if you have any questions about the content. I'm happy to answer.